Alright, welcome back. It's been a while. There's two more topics we need to cover before the next test. Those are related rates and the derivative in the natural sciences. So today we're going to be talking about related rates. So suppose we have a function that has both x's and y's or any number of variables in it, and we have another variable, t, like time, and that x might be changing and y might be changing both, not based on each other, but instead based on a third variable, time. And suppose we wanted to take the derivatives with respect to t. Well, and it's an example, let's calculate d dt of x squared minus y equals 2. Well, we just take the derivative of both sides with respect to time. And the left side is a subtraction, and the right side is just the constant value 2. Well, since the right's the constant, when we try to take the derivative, we get 0, and the derivative of the left-hand side is just, well, since we're subtracting two functions, we take d dt of x squared and d dt of y. And as we saw in implicit differentiation, the way to take d dt of x squared is to take 2x dx dt. And the way to take the derivative with respect to t of y is just to write dy dt. And so you can see we get this equation, 2x dx dt equals, minus dy dt equals 0. Now, it's important to remember that since it's not dx dx or dy dy, they don't cancel, they don't go anywhere. The dx dt and the dy dt stay around. And suppose I told you some extra information. X squared minus y equals 2 has x equals 2, y equals 2 as a solution. And suppose I told you that dy dt was equal to negative 1 there. Well, could you solve for dx dt? Sure, you just take the equation you just found and you plug in all of the pieces of information that you have. So we get 2 times x, which is 2 times 2, times dx dt, which is what we don't know, minus dy dt, which is negative 1, equals 0. So 4 times dx dt plus 1 equals 0, which simplifies to 4 times dx dt equals negative 1. And solving for dx dt, we get negative 1/4. So that if we're at the point 2, 2, and dy dt is negative 1, right, if y is changing at the rate of negative 1 unit per time, then dx dt tells us that x is changing at negative 1/4 units per time. So what you need to be able to do in order to do related rates is the following. You need to know how to read a word problem, and from it write some equations. You need to know how to differentiate things implicitly, and you need to know how to solve for missing variables. Alright, so let's take another word problem. Suppose we have a square, and the square is shrinking, and its side is changing, and it's getting smaller 1 centimeter per second. Well, when the side is 5 centimeters, how fast is it losing area? So here's an image of a shrinking square. The inner square has side length x. And so we know the area is x squared. That's the area of a square. And we also know that dx dt, that the length is changing and it's losing 1 centimeter per second. Eventually, we're going to let the fact that x equals 5 come into play because we want to know what happens when x is 5. And we want to know what is dA dt. Well, if we took the equation a equals x squared up here at the top, and we take the derivative of both sides with respect to t, the left side becomes dA dt, which is what we want, and the right side becomes d dt of x squared, and d dt of x squared is simply 2x dx dt. At this point, we can let x finally be 5, And so we get dA dt is 2 times 5 times dx dt, which is negative 1. And so we get that the area is changing when the width is 5 at the rate of negative 10 centimeters squared per second. The reason that these are called related rates is because they involve rates. You're told how fast something is changing, and two or more rates are related by some system of equations. So let's take a coffee cup. Our coffee cup is 10 centimeters tall, and it has a 6 centimeter diameter base, and we're going to be pouring coffee in. And we're going to be pouring the coffee at the rate of 1 liter per minute. And we're curious, how fast is the height of the coffee in the cup rising when the cup is half full? So let's draw a picture of a coffee cup. The base is 6 units across. The height is 10 units tall. It's 6 centimeters by 10 centimeters. And h is the variable I'm going to give to the height. Well, the volume of a coffee cup or a cylinder is pi r squared times the height. And we know that dV dt, and I've changed it from 1 liter per minute to this, which is 1,000 cubic centimeters per minute, because our other units are in centimeters. Eventually, we're going to use the fact that the height is 5 centimeters, and what we want to solve for is dH dt. So, if we try to take the derivative of volume with respect to time, we have to take the derivative of pi r squared h. Well, that involves the product rule. First we pull pi out because you don't have to use the product rule on a constant, and then we use the product rule. The derivative of r squared h is the derivative of r squared times h plus r squared times the derivative of h, which is pi times 2rh dr dt plus r squared dH dt. Now, dr dt is actually 0. Pause for a second and think about why it's 0. And now that you're back, the reason dr dt is 0 is because the radius of this cup never changes. It's always the same radius. And so if it's never changing, the derivative of a constant is 0. And since that's 0, we can cross that out, and we get pi r squared dH dt is dV dt. So dH dt equals, so now we're going to solve for dH dt because that's what we want. So we take dV dt and divide by pi r squared. Now if the diameter is 6, r is 3, and so we just get 1,000 divided by pi times 3 squared. And what we wind up getting is approximately 35.4 centimeters per minute, which is about 1/2 of a centimeter per second. So that coffee cup is going to get full very fast. All right, so here's a easier to set up problem. Once you know how to think about it, you have a rocket, and it's going to be launched from the ground up into the air. It's going to go straight up, and you're watching it from a mile away. And if you imagine that you're always looking straight at the rocket, your head is going to slowly rise up into the air. The angle that your eyes make with the ground will slowly go up, and we're curious, well, if the rocket's flying at the rate of 20 miles per minute, at what rate is the angle of your eyes changing when the rocket is a mile above the Earth? And so let's draw a picture of the rocket. If you draw a picture, what you're going to notice is that we're making a nice right triangle. The base is 1, the height is going to be h, and what we want is d theta dt. And since we want d theta dt, we need a function which relates theta to h. Now luckily, arctangent is the right formula for us to use. We know that theta is arctangent of h. Well, it's arctangent of h over 1. Eventually, we're going to let h be 1 mile, and dh dt is 20 miles per minute. But for now, the most important thing is to take the derivative of theta with respect to time, because what we're trying to find is d theta dt. So we take the derivative of both sides, and if you remember from inverse trig, the derivative of arctan of h is 1 over 1 plus h squared times dh dt. Now we're at the point where we can plug everything in. We've taken the derivative, so d theta dt is 1 over 1 plus 1 squared times 20. And the units that we're getting, the angle is in terms of radians, so the change in angle over time is going to be 10 radians per minute. So go ahead, practice setting up some problems, plugging in values, and getting used to related rates. I'll see you next video.